problem statement. We are having a step bar which having two elements, each element having the different cross-sectional area and different material properties. The step bar is fixed at one end and it will be loaded at other end by the force of 10 kN. So after solving, we will get the results as the deformation at node number 2 is 0.05 mm, node number 3 0.117 mm. The reaction at node number 1, that is at support, will be get as a minus 1000 Newton. The stresses in the element, that is at in first element we get the 50 Newton per mm square, and in element 2 we will be get the stresses as 100.5 Newton per mm square. This is the analytical solution and we need to verify this answer using ANSYS APDL. So let's start the ANSYS, and to start the ANSYS again we need to press the start key and search for APDL. Now click on this mechanical APDL product launcher and the ANSYS window will be get open within few seconds. Now you will get this window on your screen. Working directory you can able to set the job name. I am giving here the job name as a step bar, and then click on this run icon. Now you will get this window on your screen. So let's start the procedure. Again there are three main steps: preprocessor, processor and post-processor. So first we need to define the preferences, structural, okay. Then in preprocessor we need to define the element type. So click on add, edit, delete, add. Then the element for the step bar is selected as a link and it is 3D finite strain 180. Click on OK. Click on close. Then we need to define the material properties. So in material properties again go for the material models, structural, linear, elastic and isotropic. We having the material properties as E value is 200 GPa. As again this ANSYS APDL software is a unitless software, so we need to put all the data in a proper unit format. So we are inputting the force data in Newton and length data in millimeter. So the value of E is converted into Newton per mm square and we can write this as a 2E5. That is 2 into 10 raised to 5 Newton per mm square, and Poisson's ratio is 0.3. Click on OK. As in this problem we are having two materials, so we need to add the second material also. To add the second material, click on this material, new model. We get the defined material ID will be defined by number 2. Click on OK. And then again click on this isotropic and define the second material property. So second material we are having 150 GPa. So it will be again converted into Newton per mm square. So we can write it as a 15E4. And Poisson's ratio we are writing as a 0.27. Click on OK. Again close this window. Now click on the sections. So we are going to define the section for the links. So we are selected the element type as a link. So click on this link icon. Click on add. Now you need to define the section IDs. So we are having two material. So we are defining the ID for these two materials. So first will be defined as a 1. Click on OK. Then we are defining the area. So the material area is 200 mm square. Click on apply. Then again we need to define the ID for the second section. So second section ID will be defined by number 2. Click OK. And its area is 100 mm square. So defining here and then click on OK. Now minimize this section button. Now go for the modeling in create. So in create we are going to create the nodes and not a key point, because we are interested in the nodal solution. And as you can see in the problem figure, we are having 3 nodes. So we need to consider this as a first node which is fixed. This will be a second node and this is a third node. And on third node there is a force of 10 kN is applied. But we are going to input the force data in the Newton. So let's create the nodes in ANSYS. So click on nodes in active CS. again the node number given as a 1 and its value in xy coordinates. So first node is at origin, so click on apply. Second node is at a distance of 200 mm, so clicking on 200, click on apply. And third node is at 300 mm from the origin, so now click on OK. So we have created the 3 nodes. Now we need to join these 3 nodes by an element and not a line, because we have created the node, so we need to join these nodes by the elements. So minimize this nodes icon, click on elements, click on element attribute. Now check here, the material number we define by the 1 and the section number is defined by 1. So whatever we define will be appear here. 1 and 2 we define the 2 sections and 2 materials. So first element is having material number 1 and section ID 1, so click on OK. Click on auto number and through nodes and pick this 1 to 2. Then click on OK icon. So it will be get connected. Now the second element having the different material properties and different sections. So again click on this element attribute. Change here material number to 2 and section number to 2. Then click OK. Again click on through nodes. And then we need to click this 2 to 3 and then click on OK. So it will be get connected. Now we need to check this material and section IDs are properly applied or not. So for this purpose, click on this list, then elements and nodes plus attributes. You will be get this window. You can see here element 1, the material is 1 and section is 1. For element number 2, material is 2 and section 2. If you not get such types of the material number and section number, means you have not applied properly the element attributes. So you need to repeat your steps. And this element 1 is connected in between node number 1 and 2 and element 2 is connected in between node number 2 and 3. So in this way we can verify that the material and section IDs are properly applied or not. Now close this window, minimize this modeling. As we have directly connected the nodes and join it by the element, so no need to go for the machine. We are directly going to apply the boundary condition and loads. So click on loads, define loads, apply, structural, displacement. Now we have created the nodes, so click on nodes. You will be get this window. Select the first node. As the first node is fixed, click on OK and select all degrees of freedom. Then click OK. So it will be get locked and the force is applied at node number 3. So minimize this displacement icon, click on force movement, click on again on nodes, select node number 3, click on OK, and the force is in direction X. So select as it is Fx and the force data we are going to input in the Newton. So it will be 10,000 and click on OK. So the force will be get applied, and if you zoom in and zoom out, it will disappear the element. So to see the elements again, click on plot and multiplots. So you can able to see the elements again, and to see the node numbers again we have to select plot controls, then numbering and make this number on. So okay, you can see the node numbers also and elements also. So all the boundary conditions are defined. Now we need to solve this problem. So minimize this, click on solution, solve current LS. Now click on OK. You will be get the solution is done window and then close this window. Now as the problem is get solved, only we need to see the result. To see the results, click on general post processor. Now we are going to see the list results. So click on list results, nodal solution. First we are going to find the deformation. So degree of freedom solution, and the deformation is carried out in X direction. So select X component and click OK. So you will be get this window. You can see at node number 1 there is no deformation because it is a fix. At node number 2 there is a deformation of 0.5 into e raised to minus 1, and at node number 3 0.1167. So this we need to verify at our analytical solution. So you can see here the same solution will be get by analytically. at node number 10, node number 2.05 mm, and node number 3.116. By ANSYS we get 116 and analytically we get 117. So it is again nearly same. The reaction will be get as a minus 1000 Newton. So let's check reaction and after that the stresses. So remember the stresses for first node element 50 and second element 100.5 Newton per mm square. Then close this window and to check the reaction solution, click on reaction solution, select the structure force Fx, click on OK. Now you can see at node number 1 we get the 10,000 Newton as a reaction, which is equal and opposite to the applied force. Now close this window. To see the stresses we need to define the element table. So minimize this list result, and in element table, as we know that before defining the element table we need to type one command in the command prompt, that is set comma last. Hit enter key, then click on this element table, define table, then add. Now select the last as a bisequence number, select ls for the linear stresses and type one number. Click on OK. So it will be get defined. Only one element need to be defined here. Then click close. To view the stress result, click on list results, then element table data, select this ls1, click OK. So you will get the stresses in element 1 as a 50 and in element 2 as a 100 Newton per mm square. Now close this window. Again you can able to plot your results, that is the stresses, nodal deformation. So to plot the results, click on plot results, contour plot, nodal solution, degree of freedom solution, and x component displacement. Okay, so you can see here this displacement at node number 1 is 0, and at this maximum displacement which is shown by the red color and which by having the value 0.1166 mm. Again you can able to see the actual step bar. To see the actual step bar, click on plot controls, style, size and shape, make this on, click OK. So you can see the actual step bar. Click on this isometric view, so you can able to see the actual step bar and in deformation plot. So again we get the color code graph, and according to these colors we get these values. So maximum deformation will be occurred at free end, and at fixed end there is a 0 value. Again if you want to plot these stresses, click on this element table, select this ls1, click on OK. So you can see here the in element 1 there is a 50 and element 2 there is a 100 mm stress. Again if you want to see the animations, so click on plot controls, animate, deformation shape, deform plus undeform, click on OK. Now you can see the deformation of the step bar due to the applied forces. Now you can change the speed also. So in this way we can solve these problems and we'll get the same results as we get by the analytical solution. So I hope you enjoy this video and you will be able to solve the step bar problem using ANSYS APDL. Now you can stop this animation, close this window. To save the file, click on file and save. So if you click on the save as, you can able to save your file in your directories and giving the file name. So the extension of this file name is .db. So we can type here as a step bar .db and it will be saved whatever you want. So it will be drives and in directory. So I have selected the user directory, then clicking on OK, the file will be get saved. So thank you for watching. Have a nice day.